So, let us start with the distributed algorithms for deadlock detection once again. So, in the last class we had seen that there are broadly three different types of control for distributed deadlock detection, and they are the centralized algorithms, the distributed algorithms, the centralized control, the distributed control, and the hierarchical control. In the last class we looked at a couple of algorithms for the centralized schemes. We first looked at the completely centralized algorithm, where one site attempts to collect the information about the wait for dependencies in all the other sites and then constructs the global wait for graph. We saw that this algorithm suffers from the phantom deadlock problem, that is, it detects sometimes false deadlocks. Then we looked at the Ho-Ramamurthy algorithms, and in that we saw two algorithms. The first one was the two-phase algorithm, which is something like running the centralized algorithm twice and expecting that if there was some false links, then in the second snapshot they will not be shown anymore. So, but then we also realized that the same scenario can repeat itself. So, it is quite possible that false deadlocks are again detected. And then we looked at another algorithm in which there were two types of tables that were exchanged. One is the process status table, the other is the resource status table, and from every site we collect both the process status table, which gives the dependencies of the processes on resources and whichever resources are currently being held by those processes, and from the same site we also get the resource status table, which tells us the status of the resources at that site. So, which one of them are currently blocked by which process and which other processes are waiting for that resource. And then I mentioned that this algorithm, the one phase algorithm, which collects both of these status tables and then constructs the wait for graph, is free of phantom deadlocks, that is, it is a correct algorithm, and I left the proof to you. Okay. So, please try to finish off that proof. Now, under the distributed deadlock detection algorithms, in the last class I had mentioned that there are at least four popular categories of algorithms. These are path pushing algorithms, edge chasing algorithms, and then diffusion computation or eco algorithm based methods, and the last one was global snapshot collection algorithm. So, we will start today with the path pushing algorithm, and in this category there are several algorithms. The one that we will pick up for our discussion is called the Obermarks algorithm. This algorithm was used in the distributed database system called R star of IBM. Okay. So, here basically we will refer to processes as transactions. Okay. So, we will refer to processes as transactions T1, T2 to Tn. Okay. Now, typically in a distributed database system, each transaction can have sub transactions executing on different nodes of the system. So, a transaction could be that I am transferring some amount of money from one account to another. If there is more than one site involved, because the two accounts may not be in the same site, then this will actually consists of two sub transaction T1A and T1b, this one executes in site A and this one executes in site B. Okay. So, this could be that it subtracts the amount from this account and then this one adds that amount to this account. Okay. So, there is a dependency between these two, this will execute and then this one will execute. Okay. So, each of these transactions, they consist of sub transactions executing in multiple sites. Is that clear? And we assume that at a time only one sub transaction is active. That is, there is a definite order in which these the sub transactions within the transaction will take place, and two of them are not going to happen concurrently. So, T1, T2 through Tn are concurrent, but the sub transactions within a transaction are not concurrent. They will execute in some order. That order may be determined at runtime, but at a time only one sub transaction will be active. Is that clear? That is the assumption under which we proceed. So, let us look at the algorithm. So, this is a path pushing algorithm. This is a path pushing algorithm. Can I have the computer please? The slides. Yes, thank you. So, a path pushing algorithm is the algorithm works as follows. The site waits for deadlock related information from other sites, and the site combines the received information with its local transaction wait for graph to build an updated transaction wait for graph. Now, for all cycles, okay, what is this Ex? So, let me explain what is this Ex. So, at a given site SA, we have the transactions which are waiting for something. So, maybe I have T5 waiting on T2, T2 waiting on T7, T7 waiting on T3, okay. And let us say T5 is currently holding a resource for which there is a request from some other transaction in some other site. Okay. So, there is a request from some other site SB, some transaction from there is requesting this. Now, at this point of time in our transaction wait for graph, we do not explicitly put the name of that transaction here. What we do is we say that is some Ex, some external process which is waiting for this. Okay. Similarly, when T3 is waiting for some transaction somewhere, that one also goes to Ex, all right. Now, see, there can be two types of cycles. One is that there can be a local cycle, but a local cycle is a local deadlock. So, it can be handled locally only, we do not need any other information for that. The other possibility is that there is a deadlock including Ex. So, there is a cycle through Ex. Now, this can be a real deadlock, it may not be a real deadlock, right, because we have abstracted out the rest of the world with this special node called Ex, right. Now, if there is a particular path within this external world from T3 to T5, then that completes the cycle, right, and the role of the distributed deadlock algorithm is to find out whether there is a cycle through Ex, right. So, what it does is it locally looks for cycles through Ex and then it looks at which is the site on which T3 is blocked. Okay. So, it sends a request to that site to send its wait for graph, and then it reconstructs the wait for graph using the path that is received from there. So, let us look at an example. So, suppose in one site I have this T5 waiting on T2, waiting on T7, waiting on T3, and then this is in one site. So, let us call this SA, and then T3 is blocked on something. Okay. So, let us say that there is another site SB and a third site SC. So, now at this point of time, all that SA had was, it had this node EX, and there was an edge from here and there was an edge here. Now, what we do is we start looking at T3 and finding out which is exactly the transaction on which it is dependent, and we find that it is dependent on T9 here, right, and then T9 to T13 through, let us say, T6, and then there is another dependency from here towards that. So, what we had here was that for this one we had this EX and like this. Now, when it asks, when T3 asks T9 that you send me the one path from there, what this SC is going to do is, it is going to give one path through X. Remember that it can have many paths through X also. There can be another path through another set of transactions through X. So, at that point of time it sends one of them. When this one is received here, what does it do? It extends this. So, it removes this and then it says that okay, now I have T9, I have T13 from here, I have T6 and then I have EX, right. Now, what do we do then? We see who does T6 depend on, and then we find that okay, T6 is depending on T8 and T8, let us say, is dependent on somebody else outside. So, and actually what happens is, let us say T8 is dependent on T5. So, what do we see here? Here you just have local dependency like this, right. So, when we ask T8 for a path, then it produces this one, and then when we put it back here, then we see from here we have T8 and then from T8 we have T5. At this point of time, this site has found out that there is a distributed deadlock.
So, how did you know of T8? Did T6 tell you that it was T8?
Yeah, we will actually, when the sites are sending the paths, they will actually also, you will also know that what they are blocked on, right. So, you can inquire and find that out, okay, right. So, this is roughly the way in which the path pushing algorithm works. The idea is that you see these paths are being pushed, so that you can construct this, okay. So, let us look at the algorithm code. So, for all cycles,
so it will push all the paths one by one because it has only pushed one of those paths, site C. You said it has pushed only one of those paths. There might be several paths existing.
so it can push them one by one.
Push one by
Yes. So, let us see the algorithm. So, what we do is, for all cycles of the form Ex through T1 through T2 to Ex, which contains the node Ex, the site transmits them in string form, okay, like Ex T1 T2 Ex to all other sites, where a subtransaction of T2 is waiting to receive a message from the subtransaction of T2 at that site. Okay. So, T2 is waiting for something, this subtransaction of T2 is waiting to receive a message from subtransaction of T2 at some other site, right. Now, see, these are separate transactions, right. So, when I am waiting for something, it is a response from some other transaction in that site only. So, is that clear? Okay. What is a transaction? A transaction consists of several sub transactions. So, they form some kind of a dependency graph, right. So, if there is a transaction waiting at some site, that means that some of its some other sub transaction of that transaction is currently waiting somewhere, right, and that it is waiting for what, maybe getting a resource locally at that site, right. So, it is not that a sub transaction at this site is locking a resource in that site, that is not what is happening. A sub transaction at this site, if it wants to access a resource at that site, then that there will be a sub transaction in that site which is locally accessing the resource and communicating with this transaction to pass on some data, and then this one can run, right. That is how the distributed transactions will work. Okay. So, that is what we mean here, that it transmits them in string form to all other sites where a sub transaction of T2 is waiting to receive a message from the sub transaction of T2 at that site. Okay. So, this is the Obermark's algorithm. So, is it correct? Is the algorithm correct? Now, see here also it is possible that it will detect false deadlocks. Why? Because this transaction wait for dependencies are changing dynamically. So, when you actually find the cycle, that cycle may not be a real one, right. So, if you have understood the previous problems, then you will see that this has the same problem. So, though there was an informal proof given for this, later on it was proved that this is not correct. Okay. So, now what we are going to do is we will study a path pushing algorithm. Now, we will study a edge chasing algorithm. Now, what did we see here? We saw that basically what we need to see is the dependencies that are there between transactions at different sites, right. We have to follow those dependencies and see whether there is a global cycle. Now, instead of pushing the paths, if we are able to detect the cycle just by sending probe messages, small messages, then the overhead or the size of the messages will be significantly smaller, right. So, what we do here is in the edge chasing algorithm, this is Chandy and others edge chasing algorithm, this is what is done. So, a process which wants to detect whether it is in a deadlock will do the following thing. So, it says that if Pi is locally dependent on itself, that is there is a local cycle in the wait for graph, then declare a deadlock, else for all Pj and Pk such that Pi is locally dependent upon Pj and Pj is waiting on Pk and Pj and Pk are on different sites. So, there is a local dependency from Pi to Pj and from Pj to Pk there is a dependency across sites, because Pj is local, Pk is in some other site. Okay. If there is such a dependency, then send probe ijk to the home site of Pk. Okay. Is that clear? Or should we start with an example first? Okay, let us start with an example and see the edge chasing algorithm, then we will come back to the code. So, let us say that I have these sites Now, see here, suppose P1 is the initiator of the deadlock detection algorithm. It checks whether there is a local cycle, no. Now, suppose it sees that there is a dependency from P3 onto some P4 which is on some other site. Okay. So, just let me complete the picture first. Right. Now, what P1 will do if it initiates the algorithm is it will see that P3 is locally dependent on P1. Okay, there is a local dependency here, right. P3 is dependent on P4 and P3 and P4 are on two different sites. So, it will send a probe message, and what will be the probe message sent? It will send a probe initiator and then from 3 to 4. Okay. What will this side do? This side, after getting this probe message, will start following from P4, okay, and it will see whether again there is a process which is locally dependent on P4 and that is waiting for some other process in other sites. So, there are two such cases. One is that it is locally dependent on P6 and P6 is waiting on P8, and it is locally dependent on P7 and P7 is waiting on P10, right. So, it will send a probe one, see the initiator is retained, okay. The first one is the initiator of the probe message, the first argument. So, that is still 1 because P1 initiated it, and the probe is being sent from 6 to 8. So, this is probe 168, and what is this going to be? Probe 1 7 10. Okay. What does P10 see? It sees that there is no dependency, right. So, it does not do anything, it simply discards this probe. And what do we do for P8? We see that there is again a dependency, okay. So, P9 is locally dependent on P8 and P9 and P1 are on two different sites. So, what it does is it sends a probe, what will it send? Probe 191 to P1. Now, whenever a node gets back a probe initiated by it, it declares a deadlock, because now there is a complete cycle. All right. Now, let us go through the code and then we will come back to the analysis of this. Is the algorithm roughly clear? Okay. So, what does the initiator do? The initiator checks if it is locally dependent on itself, then declares a deadlock. Otherwise, for all Pj and Pk such that Pi is locally dependent on Pj and Pj is waiting on Pk, and Pj and Pk are on different sites. We send a probe ijk to the home site of Pk. Then on receiving the probe ijk, the site takes the following action. If Pk is blocked and dependent Ki is false, what is dependent Ki? It is indicates that Pk is dependent on I. Okay. If it is false, and see, if it is dependent on I, then you have already found out a cycle, right, because now I is telling that it is dependent on K and you already have dependent Ki. So, then it is then we will have a cycle already. So, if it is false and Pk has not replied to all requests of Pj, then begin. We first set dependent Ki equal to true, and then if K equal to I, then declare that Pi is deadlocked, because then you are dependent on yourself. Okay. Else for all Pm and Pn such that Pk is locally dependent upon Pm and Pm is waiting on Pn and Pm and Pn are on different sites, same thing as we did before, then we send the probe Imn to the home site of Pn. Okay. Is it clear?
Is happening like prevention because we are assuming we are finding the deadlock before execution?
No, no. Whenever a site thinks that it is possibly in deadlock, it will initiate this algorithm.
Possibly in every step it has to check.
No, 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 may not. It may not. It may have some timeout, after which it sees that okay, nothing is happening, I am not getting access to the resource. So, let me check whether I am in a deadlock. It will not be a good idea to do it for every request. So, it is like you initiate this only once in a while. Okay. Now, what is the first of all, is this algorithm correct? I mean, are we guaranteed that whenever it detects a deadlock, that is a correct deadlock? How many of you think yes? And how many of you think no? Okay. So, many of you think no, some of you think yes, and the others are undecided. Okay. Actually, the algorithm is correct. So, it does not detect false deadlocks, right. So, what we have to understand is that that you cannot get this cycle in an intermittent form, right. So, the thing is that because your probes are moving in one direction, right, you are only moving along the dependencies. So, if any of them becomes resolved at any point of time or has a potential of being resolved, then that node is not blocked, right. So, it is going to come out of it, right. So, when the probe message reaches here, P10 is not blocked, and once P10 is not blocked, there is no further probe from P10. Can it get resolved means once the probe comes here, okay, see you are sending the probe along all of these things. Okay, this is the AND model in which we are working. So, what it means is that if you have any one cycle, that itself is a deadlock. So, it is not like that P5 can do either with the resource of P6 or with the resource of P7. It needs the resource of P6 and it needs the resource of P7, right. So, it is in the AND model that we are working here. So, that means that if P6 cannot release the resource, then P5 also is in deadlock, It cannot get away by taking the resource of P7 and then it cannot complete with only that, right. So, when the probe reaches a particular site, it is either blocked or not blocked, right. Now, think of a non-deadlock situation. There will be somebody in that cycle who is not blocked, right. Otherwise, you have a real deadlock. Okay. So, what this probe does is, it along the path which it is traversing, there is no hope that these ones will be able to resolve until the ones to which the probe is sending is being resolved. So, here for example, there is no hope that P5 will be resolved until P8 and P10 are resolved, right. So, we are just following down those dependencies. So, therefore, there is no way that you will detect a false link here, right. And if any of them, whichever ones are not blocked, from there the probe does not propagate anymore, all right. So, that is how it guarantees that this is a that the algorithm is correct, that it finds out, and it is fairly simple to see that if there is a deadlock, then the probe will propagate right through that cycle and you will see, you will detect the deadlock there, right. The other interesting thing about this algorithm is the number of messages that are needed in the worst case. So, yes.
Might be P10 after dropping the probe understands that it depends on P1.
After dropping the probe,
finds out it depends on P1.
No, that cannot be possible, because
maybe P10 is in part of the transaction which is not yet dependent on P1, because we are not acquiring everything beforehand.
No. So, what you are saying is that P10 is in execution, right. It has not yet made a request for P1. Is that what you are saying?
Yes.
No. So, then at this point of time, we will at this point of time the deadlock has not yet been created, right. So, therefore, we will drop the probe. See, the point is, at this point of time the deadlock has not yet been created, but there is a potential, as you point out, that now if P10 makes a request for P1, we will have another cycle, right, but it has not yet happened. So, it is possible that P1 may resolve itself by that time. It may not happen also, it may be an unsafe situation which will definitely lead to a deadlock, but since the deadlock is not there at this point of time, we will assume that it is not there, which is true, okay. But whenever the deadlock has happened, then P10 is blocked. Now, let us analyze the number of messages that this algorithm can take in the worst case. So, can you tell me how to do that analysis? I mean, so there are, let us say, let us write down that we have, okay, let us say that we have m processes and n sites, right. Now, the question is that how are the probes sent? The probes are sent from site to site, right. So, from some process Pi in one site to some process Pj in another site, right. That is how the probes are sent. So, what is the worst case number of messages, probe messages, that you may have to send with m processes and n sites?
So we can ignore local distance.
Mm-hmm.
We can ignore local.
Locally, there you are not sending messages. Local analysis is through the local data structures. There is no messages. I am asking you that what will be the maximum number of, worst case number of messages that you may have to send in a system of m processes and n sites.
N square.
How do you say n square?
1 second.
NC2 independent of m, is it? How can it be independent of m?
Maybe you have to take average case.
No, worst case. I am asking you for worst case. So you see, this is a very interesting problem. And by the way, how many of you have done a graph theory course? You have. All right. So what are we looking for? We are looking for there are n sites. So we are looking for an n partite graph, right? The total number of vertices of that graph is m, and we want to maximize the number of edges, right? We want to find out, because the maximum number of edges are dependencies across sites, right? So we are looking for an n partite graph, because there are no edges between the we are not sending probes between the nodes in the same site. Between processes in the same site, no messages are being sent, right? So you can think of this as a n partite graph, right? And we want to see how many messages are possible, which means what is the maximum number of edges that you might have.
N by n. Each side will have n by m. In that way we can maximize the number of edges.
Yeah, so can you tell me which graph will maximize this number of edges?
N partite graph which have m by n vertices at each.
So most well balanced one,
Yes.
right? Do you know the name of that graph? You have studied this, right? The Turan graph? No? Okay, so there is a graph called Turan graph. Turan graph is a balanced R-partite graph, right? So if you look at TNR, TNR is the Turan graph with n vertices and R-partite sets. Basically what we do is we distribute these n vertices in a balanced way among the R-partite sets, and there is Turan's theorem which shows that among all R-partite graphs with n vertices, this is the one which has the maximum number of edges, right? And then you count the number of edges of TNR, that gives you the worst case message complexity of this algorithm. Right. There are some extensions of this edge chasing algorithm, and one of those extensions, okay, there are a couple of them I have noted down here. The Michel-Merit algorithm is one of them, and then there is a Singha-Niranjan algorithm. Actually this is a typo, it is a Natarajan actually, not Niranjan. This is Singha, let me correct it. So let us look at the Michel-Merit algorithm in brief. So in the edge chasing algorithm that we have seen so far, the process which initiates the algorithm is the one which detects the cycle, right? And then that process breaks the cycle by aborting itself. Right? Now that is not always the best way to do the thing, right? Because if at the same time two processes had initiated the algorithm and both of them detect the deadlock, so we may end up in a situation where both of them abort themselves, but that was not necessary. In a particular cycle, if any one of them aborts itself, then the transactions other ones can complete, right? and in the case where multiple cycles are present, it is even more complicated. There might be one process which is there in both of the cycles, and aborting that will break all the deadlocks. On the other hand, if you have two different processes in two cycles breaking the deadlock, then you are unnecessarily aborting more transactions than needed. So, what we do in Michel-Merit algorithm is we impose a kind of priority between the processes, so that the one which has the maximum priority in the end will abort itself. Alright. So, how do we do that? So, each node of the transaction wait for graph has two labels. Okay, so one of those labels is called a private label, and the other is called a public label. So, what the general the outline of this algorithm is that the algorithm detects a deadlock. This algorithm detects a deadlock by propagating the public labels in the backward direction. So, how does this work? Initially, at a node, the public label and the private label will be the same. Okay, it is some number that will be the private label and public label of that node. Every node has a unique private label, right. Then let us see how the public labels get updated. So, when a transaction is blocked, the public and private label Is this clear? When a transaction is blocked, the public and private label of its node in the transaction wait for graph are changed to a value greater than their previous values and greater than the public label of the blocking transaction, right. So, for example, that if there is a transaction Ti which is now getting blocked on Tj, right, and its suppose this one had a public label of 8, right, and this one had a public level of 5, private and public level of 5, then we will update both of its private and public level to something larger than this. So, maybe we will put this to be 9 or something like that, both public and private level. Now, the idea here is that we will eventually want the transaction having the largest label to abort itself, and it makes sense because you see this one is coming and joining the thing later on. So, this is a better candidate for abortion than Tj, because Tj started earlier, it was doing something, and now Ti has come and it has become dependent on Tj, right. So, it is better that we abort Ti rather than Tj, right. So, as and when new transactions are coming and getting blocked, their labels are increasing, right. Now, how do the labels propagate backwards? Now, when a transaction is blocked, it periodically will do the following thing. So, a blocked transaction periodically reads the public label of the blocking transaction and replaces its own public label with it. Now, let us understand what is happening here. Here I had say T1, okay, which was executing, it had not blocked or anything, but it is currently blocking a resource, it is using a resource, and when T2 wants to access that resource, it blocks here, right. So, let us say this one's public level was 5, right. At this time T2 now updates itself to 6, right. Now, let us say that now T1 wants to access some T5, some resource held by T5, okay, and T5 has a public level of 9. So, when T1 blocks on T5, what will it do? It will update this to something larger than this. So, 10 let us say, right. Now, T2 does not know that, okay. So, T2 does not know that. So, periodically it will inspect the label of T1 and update itself. So, next time when it does it, it will also update itself to 10, right. No, this is just that when it first blocks, it will give itself an ID greater than that, but later on periodically it will inspect and set it to the same value, right. Now, let us say that at some point of time T5 makes a request for a resource held by T2, right. So, it makes a request here. Now, when it blocks on T2, it will update itself. So, it will become 11, right. After some time this one will become 11, because this will periodically inspect this. After some time this one will become 11, right, and then when you see, when this one inspects and finds that it is the same as its own public label, then it knows that there is a cycle, right, then it breaks it, right. Is that clear? The one whose public label and no, there is one of these you see whose public label and private label will match. Which one here, you tell me? See, when the last dependency occurred, that is T5 blocked on T2, it changed both its public and private label to 11, right. So, when you find that your public label and private label are the same, and the ones that you are depending on have the same public label, then you know that this is the one. So, you see T5 will therefore abort. Now, see, that is fair enough, because T5 was the last one to block on T2. So, we want to unwind the thing also from the reverse, right, from the last step we want to start aborting. So, T5 will abort itself, and then it will continue once again. Is that clear roughly? Think it over and make sure that that you are very clear in your mind about how this algorithm works. Okay. So, in the next class we are going to look at the eco algorithm based deadlock detection schemes, and then the global snapshot detection.